Hey everyone, welcome back to The Explainer. So today we're diving straight into something absolutely crucial. If you've ever poked around a Kaggle competition and thought, how on earth are these winning models making such incredibly accurate predictions? Well, you're in the right place. We're going to completely demystify the math behind it. Get ready because we're setting the stage for the ultimate machine learning showdown, bagging versus boosting. Now, I want you to start by just asking yourself this. What if you had a panel of experts instead of just one? Seriously, if you're trying to solve a massively complex problem, who would you rather rely on? One solitary genius or a diverse panel? Maybe a brilliant mathematician, a physicist, and a statistician all working together. Intuitively, it makes sense, right? Combining distinct opinions yields a much better, way more robust solution. And honestly, this intuitive analogy, it's the exact mathematical foundation for literally everything we're going to talk about today. Okay, let's dive into this roadmap. We're going to break this down into 6 parts. First, the power of ensembles. Second, taming variance with bagging. Third, inside the random forest. Fourth, conquering bias with boosting. Fifth, gradient boosting. And finally, the real-world showdown. Let's get to it. Section 1, the power of ensembles, combining simple models into titans. So to give you a bit of context on why this actually matters, you should know that the top algorithms at internet giants, think Google, Facebook, Amazon, they rely heavily on this overarching concept. They don't just build one giant monolithic algorithm, no way. They combine simple models into absolute titans of prediction. So an ensemble is simply combining multiple simpler base models creatively to build a significantly more powerful, highly accurate predictive model. But here's the catch. The magic here completely relies on these base models being fundamentally different from one another. It's just like our panel of experts, right? If all your models think the exact same way, well, they are going to help each other. But if they're distinct, they can cover each other's blind spots beautifully. Section 2. Taming variance with bagging. The bootstrapped aggregation method. Okay, so our first major villain in the machine learning world is high variance. And variance is basically when your model overfits. It essentially memorizes the training data so closely that it performs terribly on new, unseen data. It's like memorizing an exam's practice questions, but failing the actual test. To defeat this, we use bagging, which stands for bootstrapped aggregation. This involves training multiple high-variance base models on random data samples with replacement and then combining their predictions. Now, what's really interesting about this slide is that bagging intentionally takes wild, erratic, deep decision trees that have high variance, and it mathematically smooths them out. By averaging their results or just taking a simple majority vote, it drastically reduces that wild variance without sacrificing their naturally low bias. It's a real game changer. Section 3. Inside the random forest, growing a forest of deep trees. If bagging is the overarching concept, the random forest is the superstar application. It basically takes the bagging formula and injects even more randomization into the process to make those base models as distinctly different as possible. Let's methodically step through how a random forest is actually grown. Step 1 is row sampling. So we grab a random subset of our data points with replacement. But step 2, this is where the real magic happens, column or feature sampling. Instead of letting the tree look at all the features, say age, income, and location, we might force it to only look at income and location. This brilliantly forces each deep tree to look at completely different aspects of the data. Then step 3, we train that deep tree. And finally, step 4, we bring all those incredibly diverse trees together for a majority vote. And there's also a brilliant side effect to this random row sampling. Because we randomly sample data to build each tree, there's always a chunk of data left out, what we call out of bag, or OOB points. These points are basically free data. Since a specific tree never saw these points during its training, this left-out data acts as an automatic built-in test set to instantly check your tree's accuracy. It's just incredibly elegant. Section 4. Conquering bias with boosting, the sequential method. So we've tamed variance, but what about the opposite villain, high bias, or underfitting? This happens when your model is just too simplistic to capture the patterns in the data. To conquer this, we contrast bagging directly with boosting. Take a look here. On the left, bagging starts with high variance, deep, complex trees, and averages them out. But on the right, boosting intentionally starts with the exact opposite, high bias, incredibly weak, shallow trees. We're talking often just a single split, known as a decision stump. Now, these weak learners start off with massive training errors. They are terrible on their own for sure. But the secret? They're designed from the ground up to work as a team.
Section 5, Gradient Boosting Explained, Learning from Mistakes.
Let's move to and see how this builds. In a gradient-boosted decision tree, or GBDT, the entire strategy relies on sequentially learning from mistakes. Step 1, you train a very basic, shallow model. And yeah, it makes a lot of mistakes. Step 2, you calculate those exact leftover mistakes, which are known as the residual errors. Then, step 3, and this is the genius part, you train the next shallow model not to predict the original target, but to predict the errors of the previous model. Finally, step 4, you additively combine them. Every new tree's sole purpose in life is literally just to fix the leftovers from the tree right before it.
Now, our source material uses a wonderful phrase to describe the math behind this. Using pseudo-residuals is widely considered a, quote, phenomenal stroke of genius, and it really is. By mathematically treating the error as the negative gradient of a loss function, gradient boosting isn't just fixing simple subtraction errors. No, it allows data scientists to plug in almost any differentiable loss function. It essentially transforms boosting into a universal optimization machine that can solve incredibly complex problems. It's mind-blowing. But wait, there is a danger here. Because GBT is so laser-focused on crushing errors sequentially, it can quickly overfit. To stop this, we introduce a number like 0.1. This is a typical shrinkage or learning rate coefficient. By multiplying each new tree's contribution by a tiny fraction, like 0.1, we intentionally slow down the learning process. We basically force the algorithm to take tiny, cautious steps, preventing this super powerful sequential learner from just memorizing the data and overfitting the whole thing.
Section 6, the real-world showdown. Which ensemble wins?
So, how do these two algorithmic titans, random forest and gradient boosting, actually stack up against each other out in the wild, operating inside petabyte-scale internet companies? And this brilliantly illustrates the difference. Look at the training style. Because random forest relies on independent trees, it is trivially parallelizable. You can throw a 100-box cluster at it, train all the trees at the exact same time, and be done incredibly fast. GBDT, however, is sequential. Tree number 2 literally cannot be trained until tree number 1 is completely finished calculating its errors. Therefore, despite using shallow trees, GBDT is significantly slower to train. But hey, training time is only half the battle. What happens at runtime when a user clicks a button and needs an instant prediction? Here is the runtime latency showdown. Random forest has to evaluate deep, complex trees, which, takes a few extra milliseconds. GBDT, on the other hand, consists of very shallow trees. A computer can evaluate these shallow if statements at lightning speed. We're talking often in less than 3 milliseconds. Because of this, GBDT absolutely dominates low-latency internet applications, where every single microsecond translates directly to user experience and revenue.
Which leaves us with a really fascinating thought to conclude our explainer today. As our global data continues to scale into the petabytes, compute time becomes a massive bottleneck. So, will the sheer brute force parallel training power of the random forest ultimately outlive the sequential, highly accurate, but slower to train elegance of gradient boosting? It's a massive question and one every data scientist has to weigh. Thanks so much for joining me on this deep dive into the math that powers our digital world. Keep learning, keep analyzing, and I will catch you in the next explainer.